Dr. Zhang Kang.
Good afternoon. It's an honor to be here. I'd like to bring your attention back to human health, namely cancer and aging. So why there is such a fear in cancer? Because it has such a high mortality. So why is actually cancer so deadly? Because when cancer is malignant, it can metastasize fast. Once it's actually metastasized, the risk of death dramatically increase. In addition, it can cause organ and tissue failure, and can cause this condition called cachectus. Essentially, it will take all the nutrients, your nutrition from the body. Now, the cause of cancer are multifactorial, meaning there's multiple causes. There's a gene, there's environment, there's a pollution, there's diets. However, I want to tell you another important factors, which is DNA methylation. The cause of cancer is staggering. We have about 10,000 people diagnosed with cancer each day, and about 8,000 people died of cancer each day. The cost of cancer treatment is 150,000 RMB, and it's increasing. I listed here top cancers in China. There's a difference in terms of the cure and also the survival rate in cancer in the United States and in China, one of which is due to the early detection and treatment. Take example of a very specific cancer to China, liver cancer. Because it is very, very hard to diagnose early, actually it's only 10% of the patients were diagnosed in the stage 1 cancer. And because the lack of effective detecting methods in the early stage of cancer, we have abysmal early detection, therefore very, very high mortality rate in liver cancer. Obviously, the earlier diagnosis, the better treatment response, and the prognosis survival will be. And this is why there's a pressing need to find a biomarker or that marker that can give you the early diagnosis accurately. I'm going to introduce you to DNA methylation, which is a modification of DNA in the human body or in the cells, and its relationship to cancer. The DNA methylation is a very, very basic modification of our DNA genetic material. It is the addition or subtraction of a methyl group on a cytosine. It's the base building blocks of our DNA genetic material. The reason this is important is because the earliest change of cancer, when that normal cell becomes a cancer cell, it had to turn on and off the genes that is involved in cancer growth. That is done by turning on or methylating specific genes in our cells. Shown on the top of these panels are the dots, are the genes that have been methylated. And you can also see that there are carcinoma in situ, those are the cancers that is still actually not metastasized or invading the surrounding tissue yet, or the cancers that metastasize. As you can see, there are distinct patterns of methylation, DNA methylation, in each cancer type and also in each stage of cancer. That's why we can actually capture those culprits and then use that to our advantage for early diagnosis of cancer. I'm going to tell you a proof of concepts in one of the studies we've done here, where we were able to identify those specific methylation markers, use them to use minimally invasive technology to diagnose cancer. And those are the 4 common cancer: breast, liver, lung, and colon cancers. Not only that, we can also tell which cancer from the different normal tissue and find where the cancer is from. If, for example, one patient has a lesion in the liver, we want to know whether it's a primary liver cancer or is actually from a metastatic lesion from colon or lung. This is not enough for the reason, in order to diagnose cancer, we have to stick a needle or do surgery to get that piece of tissue to do the diagnosis. Would it be nice if we can actually just take a tube of blood and then figure out whether this patient has cancer. David alluded earlier that Grail and other companies also looking at the cell-free DNA. Those are the DNA released by the tumor cells in the bloodstream that can be used. They can enable us to do non-invasive diagnosis, and it will give you the whole picture of the cancer tissue or sample, and then it's a dynamic, it's a real time. I'm going to use the example of using this circulating tumor DNA for diagnosis and prognosis of hepatocellular carcinoma, the liver cancer. And this is one of the large studies, the first large studies using clinical samples of 2,000 cancer patients and normal controls to conduct the studies. So in this study, we show that using the circulating tumor DNA or ctDNA, we can very accurately diagnose cancer compared from the normal blood sample or from the liver disease, such as liver cirrhosis or fatty liver disease. Not only that, we can also tell if, for example, a patient is undergo surgery. After surgery, when the tumors are gone, we can see the biomarker, the methylation marker, are now decreased. When the tumor came back, we also can see that the methylation marker has spiked up. So it gives you a real-time monitoring of the drug response. We also can tell whether this patient is from stage 1 to stage 4 cancer, and then that also can be differentiated from the normal blood samples. The only biomarker that now, if you walk into the hospital in China or United States, the only biomarker now used is called alpha-fetoprotein, or AFP. However, this protein or biomarker is notoriously insensitive in early stage of cancer. And for example, if there's 100 liver cancer patients, only about 60 at max will be able to diagnose with this cancer marker. Our study can show over 90–95% accuracy in sensitivity and specificity in diagnosing cancer. In addition, we also can use those methylation markers to predict when the patient just walks into the hospital, whether this patient will have a bad prognosis or good prognosis, meaning what's the chance this patient can survive for 5 years or 10 years. And once we draw these lines, for example, the top line, the blue line is the one that gives the patient much better prognosis or survival advantage. Then we can plan our surgery and also our treatment. For example, for the red lines, we want to do it more aggressively to kill off those patients with cancer cells. These studies show that we can real-time monitor the tumor load, because the tumor load, the top panel shows the tumor load. The tumor load is, when it's higher, that means there's aggressive tumor, and we have to hit it all we can with different arsenals. And the lower one shows different patients. On the left side is the patient responding to the therapy, and the right side, when the line is going up, means the patient is not responding, the tumors are coming back. So those are all good examples of how we can use this information for advantage for combating tumor. This is a comparison of different ways we can actually look at the tumor and also diagnose tumor. The DNA methylation markers will have advantage to look at some of the in situ, meaning the cancer hasn't metastasized yet, or early stage, late stage cancer, can use for monitoring. It can be non-invasive, and it will be based, it also can figure out which cancer is from which tissue, which is very important. There are many other ways to diagnose cancer. What I want to do is to emphasize early detection, because I will show you slides. Essentially, early detection is the key for us to cut the cancer cost and also cancer death. These slides show that the DNA methylation can roughly detecting less than 1 million cancer cell release DNA. That translates into something like a pea-sized cancer tissue. This is not sensitive to be using or detected by conventional imaging studies. If you go to a hospital, they will perform MRI, CT scans, and X-rays. Those are not going to be able to be sensitive enough to pick up those And those at least should be something like a thumb-sized lesions. Those lesions usually carries about 5 million to 10 million cancer cells. So our technology has the potential to scale down to hundreds of thousands to about 1 million, less than 1 million cells, which give us a huge advantage on this. This slide is very important. That tells me to tell you that on the y-axis is the survival rate. The x-axis is the staging of the cancer. You can see that there's a much higher survival rate in the left side when the patient is stage 1 or stage 2 cancer. However, when the curve moves to the right side, there's abysmal 5-year survival rate. If you can imagine, we can shift the detection of a cancer from the late stage, the stage 3 to stage 4 to stage 1 to stage 2, we can dramatically, dramatically improve the survival of patients. This is particularly urgent because in China, when a patient walks into the hospital, at least 60% of those patients are now diagnosed with cancer in the late stage, meaning in the stage 3 or stage 4. Not only those patients will have very, very poor prognosis or survival, also the treatment, the options, and also the cost of treatment is very, very high. So the benefit of shifting the diagnosis to treatment to the early stage is very, very evident. So I propose that now we are in a stage where we can actually, together, we can cut the tumor death in half just by simply doing the early detection of treatment. And I think there's wonderful works done in Grail and also other companies here in the United States and also in China. And together, I think by combining the technology, we should be able to achieve our goals. And then have a routine blood draw and also a routine check for cancer, just like you go into your hospital or clinic for an annual health check. Another important point is actually the stage 1 cancer can be, because localized, it can be really surgically removed, and then that actually equates to a cure. It's very rare you can cure cancer unless you can actually acting at the stage 1. In order to achieve these goals, we have not only did the studies in liver cancer, we now have actually developed methylation markers in 20 all solid and also leukemic cancers. So we're going to try to use this to using machine learning and also try to finish some of the 500,000 samples in our freezer in order to develop a huge database, and then to use this to develop, construct, we call it pan-cancer markers that will be used for detecting all the cancers. I'm going to shift my gears, tell you another story, but this story is connected. Aging. After we solve the cancer problem, you're probably going to actually worry about aging, because this is another problem that we have to face. You have heard the wonderful stories and the research done by Dr. Tony Weiss-Corey. Have you ever thought about why we get old? And when we were born, unfortunately, we're destined to die. And what is in our body that tells us we can only get old, we cannot get young? And you have seen this picture, so this is actually very, very desirable thing to figure out how we can stay young. There's also that need for aging research, because aging is the #1 cause of cancer, cardiovascular disease, diabetes, etc. And many patients that get old, 92% in 65-year-old, have at least one type of chronic disease. In addition, our population is constantly getting old. Obviously, there were many, many markers, what we call, try to figure out what is this biological clock that make us getting old. And obviously, there was very important applications for this, including predicting some of the onset of disease, diagnosing age-related disease as well. And there are examples of biomarkers such as telomere length and immunological markers or protein markers. I want to tell you a new marker, which is a methylation, DNA methylation-driven marker. And if you think about it, again, coming back to methylations, you will have to think about the methylation as an on and off switch on many things in our body. If you would think about why your ear, your eye is different from your arm, why is your heart is different from your liver, that's all because it's controlled largely by gene expression. The different genes are expressed or present in different parts of your body or tissue, and this differential presence of genes are controlled by methylation. So you can turn on and off your genes, give you a distinct tissue. And through the studies or genome-wide methylation studies, and we're able to, again, looking at some of the important markers in methylation. And it turned out that this methylation marker we find is present in all the cells and all the tissues. It's constant ticking. It doesn't matter it's a dividing tissue, such as our blood cells, or it's a brain, which is non-dividing cells. It's just as if we know, our cell knows that we have to get old. There's a ticking clock that is inside our body, in our cells, going through the motion and push us to an older stage. And of course, that there are people who are younger than their age. There's also people who are older than their age. And those are actually controlled by the lifestyle and also by disease status. What we know now is diabetes is one of the biggest accelerators for aging, along with mental health and stress. In addition, there are also differences. For example, female is always, the ladies are always 5 years younger than the man. And also the cancer cells in the body are always older than the surrounding tissues. This clock now has been replicated in 90 studies with 20,000 samples with a p-value of -500, meaning this clock for sure is running in all of us and in all the cells, in all the tissues. This is a different clock than the clock that won the Nobel Prize of Physiology and Medicine this year. That's a circadian rhythm clock, meaning to tell us is it daytime or nighttime. This clock, a methylation clock, is running to push us from the adults all the way to young adults, all the way to the older age. I told you that there were many factors that is influencing this epigenetic or methylation biology clock, and the genetics obviously is involved, and the diet we know is involved. And then in addition, mental stress, exercise, and obviously, the people will want to know whether we can use exercise or pharmaceutical compounds that can reverse aging. So what we can do now, we show in our laboratory that we can manipulate this biological methylation clock in cell culture and in animal models, and we can accelerate or slow down the clock. I'll give you an example that we can take a 90-year-old cell and then introduce those stem cell factors that turn them into pluripotent stem cells, such as they're equivalent to the embryonic stem cells. When we measure the clock, we can universally turn the clock back to 0. Conversely, if we take a cell line from the premature aging and measure, those are the patients that will die before they turn 20 years old. However, if you measure their methylation clock, the clock is always being 60 to 100 years old. I mean, the clock is really the readout and the driver for our human aging. By our experiments, by subtracting and also genetically manipulating the clock, sometimes by CRISPR technology, gene editing, sometimes by pharmaceutical interventions, we show we can really dramatically slow down or accelerate the clock. So I would expect that in our lifetimes, the human being can live more than 150 to 200 years. Obviously, there are also other social consequences. We have to actually put more people on the moon or in the Mars. So I want to summarize my talk to tell you that methylation, DNA methylation is a fundamental cellular life mechanism that is involved or intimately linked to cancer and also aging. And we can use methylation markers in liquid biopsy in the blood, and that can actually use for early screening, detection, monitoring of cancer, and hope that can actually dramatically cut down the cancer death. The methylation biological clock is also very important in the aging process. We're hoping to use this to predict aging, to combat age-related disease, and to undergo healthy aging. So again, the goal is to, together with the new technology, methylation markers, we're hoping that to cut the cancer death by 2027 into half by performing early diagnosis and treatment, and have life extensions to about 150 years to 200 years, and use this to prevent age-related diseases. I want to take this opportunity to thank Tencent and Nature again, and also thank the past and current members of my laboratory and also my collaborators. Thank you.